This is a short talk about a fundamental duality that runs throughout the exact sciences, starting with logic and mathematics through to biology. And in that sense, I would say it's a metaphysical duality. And here is a picture of the two sides of the duality. And category theory in mathematics is the only place where both sides of this duality are really developed. That the duality can be seen as a duality between subsets or partitions and partitions. And here's a quote from one of the great category theorists. uh, Dual notion of a part or a subobject or a subset is a notion of partition. And the usual notion of logic is the Boolean logic. And Boolean logic is normally presented as the logic of propositions, but it's really the logic of subsets. And propositional logic is a special case. And the other side of that uh, duality is, since subsets are dual to partitions, a partition on a set is the same thing as a equivalence relation or even a quotient set. There is a logic of partitions. And all these notions are mathematically developed within category theory. But when you start to apply them, like, okay, since we have a logic of subsets and we know from category theory subsets are dual partitions, we should have a logic of partitions. But this side of the duality, aside from the math side here, is very underdeveloped. And I'll explain that as we go along. So we start with the notion of normal Boolean logic, and usually seen as the logic of propositions, but really should be seen as the logic of subsets. The dual logic is the logic of partitions. And to have a logic, you need to have the logical operations, join, meet, and implication in particular. And the operation on partitions on a set, join and meet, they were known in the 19th century by Dedekind and Schroeder. But no new operations were defined on partitions in the 20th century. And to have a logic, you at least need, in addition to the join and meet, you need to have implication. And so the real logic of partitions or logic of equivalence relations did not develop in the 20th century. And the notion of implication and then the other logical operations only became developed in the 21st century. And I published the system of partition logic first in 2010, and now we're 15 years later, and still logicians seem almost unaware of it. There's no paper on partition logic has been published by other logicians since 2010. So my point here is that this whole side, aside from the first one here, is totally undeveloped. And so what I'm giving you today is a brief overview of this other side of the duality. And at the more granular level, we would say that a subset is made up of elements, or what we might call its, and a partition is made up of what we will call dits, which is an ordered pair of elements that are in different blocks of the partition. So this will become clear. But before we leave the logic of partitions, here's a book on it. Just came out. Two major applications, which are to information theory and to quantum mechanics. So let's now go to the quantitative version of these two logics. So the partition is on a universe set U, which we'll take to be finite, is a non-empty a set of non-empty disjoint subsets called blocks, and they sum to U. So the universe set is divided up into these blocks that are disjoint, and their union is all the set. Distinction is an ordered pair of elements from two different blocks. and elements of a subset are dual to distinctions. So here is a table that to convince you that elements are dual to distinctions of a partition. And you can see that they play the correspondingly dual roles in these two basic lattices. So the lattice of subsets, the usual Boolean lattice, and the lattice of partitions. Now the partial order, the PO is partial order in the Boolean lattice, is just inclusion of elements, that S is included in T if all the elements of S are elements of T. And the partial order in the lattice of partitions is called refinement. So the less refined partition sigma here and the more refined partition pi means that you take some of the blocks of sigma and you break them up into smaller blocks and you get the blocks of pi. So every block of pi is totally contained in some block of sigma. That's the notion of refinement. But that turns out to be completely equivalent to just saying the set of distinctions of sigma, the set of ordered pairs in different blocks, is included in the set of distinctions in pi. So the partial order is inclusion of elements. Partial order here is inclusion of distinctions. So we see that distinctions and elements are dual concepts. Same thing for the join. The join in the lattice of subsets is just a union of elements. And the join for partitions, the join of two partitions is the partition whose blocks are all the non-empty intersections of the blocks between the two partitions. So you have blocks in the two different partitions, and you take their intersections, and the ones that are non-empty will generate a new partition called the join, and its set of distinctions is just the union, again, of the distinctions of sigma and the distinctions of pi. So once again, union of elements, union of distinctions in the join. Similarly, the top of the lattice is all elements in the Boolean lattice, and the top of the partition lattice is the partition called the discrete partition, symbolized 1, where all the blocks are singletons. So everything is distinguished from everything else, and everything is a singleton. So all distinctions that can be made are there. And at the bottom of the Boolean lattice is empty set, no elements. At the bottom of the partition lattice is the partition which has only one block, which is namely everything. So it has no distinctions. There's no two blocks to have an ordered pair, one element in one block and the other. So you get, again, complete parallelism between elements and distinctions. So at the most granular level, the type of duality we're talking about here is between elements and distinctions. And but we want to move to the quantitative version of this. So the quantitative version of the logic of subsets, which was developed by Boolean probability or Laplacian probability, is you just take the number of elements and you normalize it. So the probability of S is the cardinality of S divided by the cardinality of the underlying set. And of course, the interpretation is if you take a random draw from U, you'll get that's the probability of getting an element of S. Here we're assuming the elements of S are equal probable. But this is where probability theory starts, and then you generalize it by taking different point probabilities and so forth. So now we know the elements are dual to distinctions, so you make exactly the same moves for the logic of partitions to get its quantitative version, and that's called logical entropy of a partition. It's just the normalized number of distinctions. Here you normalize, since distinctions are ordered pairs, you normalize by the set of all ordered pairs, which is the Cartesian product. And that gives you the notion of logical entropy, h of pi, logical entropy of a partition. Here you have the logical probability of a subset. Remember, subsets are dual to partitions. And the interpretation here is just a two-draw probability of getting a distinction rather than the one-draw probability of getting an element of S. So here are your two lattices for a universe set of 3 elements, ABC, and the subset lattice has the empty set, the bottom, the universal set at the top. And if you think in terms of your classical Greek notions of substance and form, then you start with zero substance, and then you have, if you move up, then you have a creation of these elements here. So it's like creation ex nihilo. But everything is fully formed. You see A, B, and C are all perfectly well distinguished. There's no becoming of them aside once they come into existence. So substance and crease is always fully formed. You get the dual thing over here in the partition lattice. You start off with all the substance at the bottom, but no form. It's not informed by any distinctions. Remember, the information here is distinctions. So, and then you start with all the substance, but no form, and then you inform them by making distinctions. So information is defined as distinctions in biological entropy until you get to the top, which is this discrete lattice, discrete partition where everything is distinguished. All the distinctions that can be made have been made, so every block is just a singleton. Now, another way to think of this more metaphysically, and it is a single element, like an element of a subset. And once you're given one element, then what are the sort of questions you can ask? And the basic question you can ask is, does it exist or not? Or in other words, is it in a subset or in the complement of the subset? That sort of thing. And that's the sort of questions you ask in Boolean logic. But for partition logic, it's you've got a ordered pair. And once you get an ordered pair, then you have a different sort of questions you can ask. You can say, are they the same or different? Identity or difference, equivalence or non-equivalence, distinctions or indistinctions. And so those are the type of questions that dominate this on the one side of the duality and this on the other side of the duality, symbolized here by these two different lattices. And this is all developed in this book, New Foundations of Information Theory, founding information theory on the notion of logical entropy rather than the better known notion of Shannon entropy. And so the whole book is comparing the two and showing that the more natural notion of information is distinctions and that its quantitative version is logical entropy, and the logic of it is the logic of partitions. So now we move to physics. Now we go to, we've done the quantitative version here. We're moving to physics. And so classical physics is here, all on this subset side. So the major point I'm making is that we have developed this side very extensively, and this side is almost undeveloped. As I just said, logic partitions is essentially unknown to most logicians. The quantitative version, logical entropy, has gotten some attention, some publications on it, but largely unknown. Most people just think of entropy as being Shannon entropy. And quantum theory turns out to be on this side. So the difference between classical physics here, quantum theory over here, is the notion of definiteness versus indefiniteness. And in classical physics, the notion of reality is our standard notion of macroscopic reality. And it's characterized by Leibniz's principle of identity of indiscernibles. So as if you had proposed two different things like Venus and the evening star. And if they are different, then the idea is there must be some predicate that applies to one and not the other. And if you have two purported entities where there's no predicate that doesn't apply to one or the other, then they're indistinguishable or indiscernible. And Leibniz's principle says, well, then they're identical. And so another way to say that is that classical reality is definite all the way down. If you go down deep enough, you'll find some predicate that separates two different things. And if you don't, then you don't have different things, that the Venus is the evening star. And quantum theory is different. Quantum theory, you have this notion of indefiniteness, and that is exactly what is modeled mathematically by the logic of partitions. Things that are in different blocks of the partition are definitely different. Things that are in the same block or equivalence class are equated and are indefinite. So to get a grip on understanding quantum mechanics, it's pretty well known that the key non-classical notion in quantum mechanics is the notion of superposition. The superposition of two states is another state, which is hardly true in classical mechanics. Then the question is, well, what do you mean by superposition? In the mathematics of quantum mechanics is using the complex numbers. The complex numbers are the natural mathematics to describe waves, is each complex number in the polar representation as an amplitude and a phase. And so what is usually done is that people think of superposition in quantum mechanics like this picture here, where you have two different waves and they add together and get a wave that's just as definite as the two waves that make it up. And that is wrong to understand quantum mechanics. That's the classical notion of superposition. Definite plus definite gives you another definite wave. Quantum superposition means that when you add a definite to a definite, in other words, an eigenstate to an eigenstate to get a superposition, that is something that's indefinite between the two definite eigenstates. So here's a picture of that. So we have two triangles here. We have the plus sign added together. And wherever they differ, they become indefinite because they differ there. Where they're the same, that can stay definite. So the A angle, the A opposite side is still there, but the sides where they differ become indefinite. So it's not like the sides become doubly labeled, like a double exposure photograph or a particle going through both slits in double slit experiment. There are indefinite. So that is one of the big roadblocks to understanding correctly quantum mechanics is interpreting superposition. Definite plus definite is indefinite, not like this. So water waves are like this, sound waves are like this, electromagnetic waves, classical wave theory is all like this. That is not what quantum superposition is about. It's about indefiniteness, and that is what is measured in the logic here. So here is a picture here, and most quantum theorists, when they understand superposition, they realize that the superposition state is not definite until you measure it. It's not like it has a definite state and you just don't know it, and then you measure to find out what it knows. It's indefinite until you measure it, and then it takes on a definite state. That means there's some sort of reality to a quantum particle that is indefinite. And this best way to visualize this is to think of an iceberg where the classical fully definite part is above ground and the indefinite part is down here. Or to think of it here, I've got a lattice of partitions on a 4-element set where I've simplified, taking away the innermost curly brackets. So just a juxtaposition here means they're in the same block. So like A, B, and C are in one block and D is in a block here. So here is the underwater part where you have, in each of these states, you have some superposition, some double state or triple state or quadruple state here. So this is like the states of one particle can have 4 different states in this ultra simplified model. But here is the classical world. So the distinct discrete partition, everything's distinct. So this is like the classical world above the water here. This is like the quantum world. So every quantum theorist that realizes that state doesn't have a definite value is in effect positing this indefinite reality, this under the water part of reality. And that's very difficult to imagine because our whole sense of reality has evolved to think of everything as being definite all the way down and not in a state of indefiniteness. So that is why the problem of interpreting quantum mechanics has been delayed about a century, because it's kind of hard to think of this whole notion of reality here that is accommodating states of indefiniteness and is different from our classical world. We can't fit it in to our classical world. So this is all developed in this book on partitions, because that's the mathematical notion to handle indefiniteness. Partitions are equivalent solutions. Objective indefiniteness, it's not just that we don't know the value, doesn't have a definite value prior to measurement. And that tells us how to interpret quantum reality, this objective indefiniteness interpretation. So that's physics briefly. And now we go to the last, life sciences, where once again, this is the side that's developed. This is the side that is not developed, except in the case of category theory. So the basic mechanism in your usual treatment of biology is selection, Darwinian selection, the selectionist mechanism. But there is a dual mechanism, which are called generative mechanisms, and they can be defined as mechanisms that implement a code. And here we have two examples of opposites. Remember, in category theory, the duality is reversing the arrow. So here you got two different tree diagrams just reversed. Here is a selectionist mechanism, like a single elimination tournament. You have all these teams, and all the teams have to exist in order for them to compete against each other, red in tooth and claw. And each competition gives you a winner, so the switch goes one way or the other, and finally you get to a winner. So that is example of a selectionist mechanism, single elimination tournament. Here is the typical representation of a generative mechanism. A mechanism implements codes. The root is like the bottom of the partition lattice, where everything is blobbed together, not differentiated. And then you start receiving a code that says, take the 0 branch or take the 1 branch. It doesn't have to be binary branches, but we're just making it simple here. And then you get 3 different letter codes come in. And that takes you down to then one of the leaves, which are the definite. These are your fully definite things. So these are, if you're somewhere up here, then you're still indefinite and working your way down by making distinctions. In other words, you're receiving a code. Code makes a distinction. Take this branch rather than that branch, or get a 0 or 1 and makes a distinction. So in terms of our lattices, here they are. In selectionist mechanism, you start off with everybody, and then they fight it out, and you end up with something, the survival of the fittest here, who wins the tournament or something like that. Whereas in the generative mechanism, it's the opposite. You start off with everything blobbed together, and then you make distinctions, and then you might end up with the C here. So you have like 2 different ways to determine the same thing by generative mechanism, starting with the root where it's all together, or starting here where you have all the teams together and then they eliminate until they get down to that. So here's another way to represent it. Selectionist determination of this outcome. So you have all these different codes, we'll say, for the 8 different teams. And then some teams get smaller. They start not as fit by the fitness requirements of the environment, say, and smaller and smaller until the one that survives dominates. So that's a selectionist determination of 0, 1, 0. And here is the generative determination of the same thing. So here I put plus signs in here to remind you of like a superposition state in quantum mechanics. And then you like measure the first position, 0. So you get all the ones that have 0 in the first position. So you eliminate this part of the tree. You go to this part of the tree because you took that 0 at the first branch. Then you, at the second branch, you get a 1, or you measure it here, you get a 1. And that gives you these 2 remaining possibilities. And then you finally get a 0 at the last branch, and that takes you to this. So you get 2 different ways, the selectionist way and the generative way. So these are the two dual mechanisms in biology that comes out of this whole analysis. One of the great generative mechanisms, of course, the RNA DNA mechanism to implement, in this case, the genetic code, and you can describe this moving down the tree as the join of partitions. So when you join partitions, you get these smaller blocks that are more definite. And here we have a partition with 4 blocks. Each one has a code attached to it. And when you take the join of that block and this block, then you get 4 times 4, or 16 possibilities. And then you take the join again with third block, you get 4 times 16, or 64 possibilities. And so those are the 64 different things coded by the 4 letter genetic code. So to get the code for any particular one, you just follow its blocks. So here is something called TR4, and its first letter of its code is A. Here it is here. So the second letter is C, and the third letter is G. So all genetic codes can be described, all instantaneous codes in coding theory can be described by this intersection of partitions that where each of the blocks is labeled as 0 or 1, or in this case, 4 different possibilities, and you're moving through until you get to a specific leaf, and the trail A, C, G gives you the code, how to get to that leaf, how to implement that code. And this is what the DNA, RNA. Another example of a generative mechanism is the stem cell. The stem cell is indefinite. It's the root of the tree, like the partition at the bottom of the lattice, and then you start making distinctions, and then it makes all these different things. So once again, you get this tree root, and all the leaves on the tree that can be developed by making distinctions. Another example is Chomsky's generative grammar. And here the question is when a child learns a grammar, it's a credible process that goes on when a baby getting all this very impoverished linguistic inputs, and yet somehow intuits or gets this grammar. What's the internal mechanism? And so Chomsky's idea, which was put it bestly by this philosopher James Higginbotham, is that it's like these switches. It's like you're setting the switches here, and here you have like the mechanism that can generate 8 different grammars. And when the child hears linguistic input, then it sets a switch one way, and and another way, another way. And so by the end, the child has gotten that specific grammar. If you tried to do it this way, then all the possible grammars would somehow have to be actual. Remember, to have a tournament like that, you need to have all the actual things to interact. So the mind of the child would have to have all possible human grammars somehow there, and then sort them out as they hear the language around them. So some of them would be more and more selected until you get one. That would have an enormous computational burden to have somehow the child have all human grammars in the baby's brain, and then sort them out according to what they hear. And so Chomsky argued against that, and said it has to be a generative mechanism where the switches just get set, and then can generate each of these grammars as the leaves on a tree as you move down that tree. And so this is what Chomsky says here, and I won't repeat that. So this was a short talk. All I wanted to tell you about is this duality: 2 sides, fully developed mathematically in category theory, which gives you the architectonic of mathematics itself. These 2 concepts go throughout mathematics. The logic on this side is the logic of subsets. The dual logic is logic of partitions, which has been developed recently. The quantitative version here is probability theory, and the quantitative version here is information theory, in particular the logical information theory or logical entropy. And this development here allows you to understand indefiniteness, which is a key to getting some grip on understanding the reality underneath quantum mechanics. And then in the biological realm, it's generative mechanisms versus selections mechanisms. All these forms are very underdeveloped. These are the forms that are actually developed. And quantum mechanics is, of course, developed as a mathematics. and as a physics, but not as an interpretation as to how do you understand indefiniteness, and then you see how it comes out of this metaphysical framework of handling the notion of indefiniteness, becoming more definite by making distinctions. So there's a book in progress there, but this is just meant to be a introduction to this fundamental duality that spreads throughout the exact sciences. Thank you very much.